I must not have gotten it fixed last year. Okay, so we're going to continue with the shell method today, except now we're going to be rotating about axes that are not the x and y axis. Okay, so I have a picture here of a region, f of x and g of x, and we're rotating it about the line x equals a. Okay, so we are still going to work with 2 pi times radius times height times thickness. Okay, our thickness is always going to be our dx or our dy. Okay, our height is always going to be that top minus bottom, right minus left concept. But our radius is going to change when we are rotating about an axis that is not the x or y axis. Okay, so I'm going to draw a rectangle in here. Okay. Our radius is always going to be the distance each of those rectangles are from the axis of rotation. Okay, so I want you to go ahead and brainstorm at your pod. How is the radius going to change when we are no longer rotating around, in this case, the y-axis? Go ahead and check.
It's like when you're on the axis,
All right, so what do we think? How is it going to change? Let's see. Pod 1, what did you guys talk about?
Wouldn't you do like the same thing you did last time with like, maybe like 10 minus, or something like that?
Okay, so we're going to subtract out, what are we subtracting though?
The distance?
Okay, because you're on the right track. You really are. Okay, this is going well. So we need to do something with a, and we need to subtract something, right? So here, let me give you this picture. This would be our new radius in this picture. Okay, that would be our new radius, right, of that shell. Okay. So pod 2, Marcus, you got really excited there. What are you thinking? What are you thinking our new radius would be?
Oh, I don't know. I just said it would be the distance from the line to the outside.
Like this rectangle?
Yeah.
So this line to the rectangle?
Yeah.
Yes. Okay. How do we describe that? Pod 3.
so the a minus x.
Pod 3 said a minus x. Thoughts? Okay. So we know that this distance right here is x, because that's what we used to use for our radius. Okay? So when we take a minus x, we have that radius that I have laid out right there. Now, word of warning, it is not always going to be a minus x. It's not always going to be a minus x. Well, what else could it be? X minus a, it depends what's to the right and what's to the left. Okay? Right now, a is more positive, what we're rotating it about, so we are writing a minus x. But if that axis of rotation was to the left of our rectangle, then we would have to do x minus a. Okay? All right. Do we write down what we needed to from this information? Okay. So now here is our first example. We're going to do 2 or 3. Okay. We're going to rotate the region bounded by 4 minus x squared, x equals 0, y equals 0, about the line x equals 2. Write down what you need to and come up with a picture for me. Okay, does your picture look like my picture? Okay, and we are going to rotate it about the line x equals 2. Now, in my opinion, I think this is easiest to leave in terms of x, okay? And if that's the case, if we wanted to do this problem in terms of x, we would make vertical rectangles with thickness dx. And since those rectangles are parallel to our axis of rotation, we will be using the shell method. Okay. Okay, so we know that the shell method, 2 pi r h thickness, okay? Our height is going to remain the same for our shells no matter what. What is the height of that rectangle? In this case, the height of this rectangle, we would say, is what, Will? Okay. Now, our radius is going to be different. Remember, our radius is always from the rectangle that we draw to the axis of rotation. Okay. So, rectangle to the axis of rotation, please keep in mind who is more positive, the rectangle, or where the rectangle is, or the axis of rotation. Okay. So, CJ, how would we describe that? What's this distance right here?
Minus a.
Okay, who's more positive? The rectangle or x equals 2?
A minus x.
Okay, and instead of a, we can write 2 minus x. Subtractions are a little wonky. Okay, so our radius is 2 minus x, because we have that right minus left coming into effect. Okay, and then of course our limits of integration would be 0 to 2. Okay. Questions on that setup? Yes.
So if that was like x equals -2, then it would be like x minus 2 then.
Well, if it was x equals -2, you would have x equals -2. Do you see what I mean?
Yeah.
Okay. Okay. All right. Math 9. Tell me the volume. What?
45 over 3.
All right, we're going to check Henry here. Okay. And Trevor, our next example will have an x equals a equation. Okay. Henry got 40 pi over 3. See if he's right. Yes, yes, yes. Yes, yes, yes. Okay. 40 pi over 3. Make sure you can get there. All right, next region. Whoa. Okay. Our next region, we are taking 3x minus x squared and revolving it around the line x equals -1 to generate a solid resembling a bundt cake. We're all hungry now, right? You know what a bundt cake is? Yes. But it's like flat. So it looks like a very large donut, but sliced in half so it sits flat.
Have you been to Nothing Bundt Cake before?
Yes.
Those are like so amazing.
They have like mini ones too, right? They're like little bundt cakes. Okay. I want you to focus on writing down what you need to and drawing the picture. Okay? Like I said, if we didn't have those darn snow days, I would make you a bundt cake and we would find the volume of it.
Oh, good work.
It's very sad.
I think the snow days are worth it.
I think next year we crash a Calc AB class and join them.
Okay.
We're juniors.
Okay.
You would join them.
Terrible.
Or maybe we can do that with the seniors graduate. We will have like 2 weeks. Okay, so can somebody give me some advice on graphing 3x minus x squared?
Graph the zeros on the next slide.
What are you going to say, Joe?
0, 0, 0, 3.
Okay, the zeros are 0 and 3. And then we guess the height, because it doesn't matter what the height is. It really doesn't. It really doesn't matter what the height is. But if you wanted to be precise, we know the vertex is in between 0 and 3, so if you plug in 1.5, you can get the exact height. But okay. So here's our region that we are rotating about the line x equals -1. Okay? For sure, the only way we can do this is in terms of x. Because we're not going to go through the work of solving this for x to write it in terms of y. It's not going to be pretty. Okay? So, going and finding the volume in terms of x is going to be our best option. Okay? Which means we have a parallel rectangle that we're revolving around x equals -1, so we're using the shell method. So we have 2 pi integral of r times h times thickness. Okay, let's talk about our height first. That's always the easiest. It's the height of our rectangle. Okay, the height of our rectangle. Michael, what would it be? Good. Now, when we talk about the radius of these shells, we're talking about this distance right here. Okay, so that distance, Eli, how do we describe that?
X plus 1.
Okay. X plus 1. Okay, we can think of it as x minus -1. and Eli just went ahead and said x plus 1. You can think of it as x plus 1 too, because you know that this distance to the y-axis is x, and then you go one more, right? So x plus 1, you can think of it that way too. Okay, both ways work. All right? And then our limits of integration would be from 0 to 3. Those are the zeros that we have. All right. Can you find me that volume of the bundt cake? How much cake do we have to disperse?
22.5 pies equal worth of 1 bundt cake.
22 and a half. 22 and a half pies to equal 1 bundt cake. Okay. So there's 15 of us. So each of us would get 3 pi over 2 worth of cake. So depending if we're talking about square inches versus square centimeters, it could be a lot of cake or a little cake.
Or square feet.
Okay. Last example. X equals y minus 2 squared and x equals y equals x. Same difference. We're going to rotate it about the line y equals -1. Your job for me is to draw a picture. Don't reference your calculator, draw a picture on your own. Michaela, can you describe that parabola to me? Which way is it opening? It's opening to the right. And so then what do we do with that 2? Which way is that shifting it? Down? Let's see. If we plug in -2 for y, what do we get for x? Okay. So does that match that point? Okay. So try, instead, maybe if we try shifting it up, when we plug 2 in for y, what do we get for x? 0. So does that match that point?
Yeah.
Okay. So I know that, and I know that Michaela is not the only person who was thinking that this was shifted down. Okay. If you're unsure, okay, because there is uncertainty in your voice, maybe it's that too. Okay, if you're unsure, take a couple points to test, so that you know you're graphing it the right way. All right. So this is our region right here. Okay, now let's talk about the benefits of the shell method. Some of us are really into that disc washer method. Why is the disc washer method not a good choice?
pick top, bottom, you have two different bottoms. If you pick right, left, you have two different lefts.
Well, if we pick top, bottom, we have the line here, but the what would be a square root here. Now, if we pick right minus left, our left is actually consistent because this is all one equation, the parabola. Okay, so right minus left, we do have consistency there. All right, so a horizontal rectangle is better for us because we only need one integral. All right, so 2 pi r h thickness. The height of our shells. We look at that rectangle and the height of each of those shells we would describe as what?
So that would be the y minus y minus 2 squared.
Okay, good. We're talking about, and it feels more like the length of a rectangle, right? Which is, so it kind of sounds weird when I say height, but how long is that rectangle? Right minus left. Okay, that's the height of each of those shells. Okay, and then the radius is from the rectangle to the axis of rotation. So our radius, we then could describe as what, Callie?
Would be y plus 1.
Callie asked, would it be y plus 1?
Yes.
Doing some head nods, yes. You could either think of it as our rectangle is our y distance minus our axis -1, or you could think of as the rectangle is y distance from the x-axis, and then there's another 1 unit to go, that axis of rotation. Okay? Ooh, limits of integration. Limits of integration. 1 to what? 5? 4? 2? Oh no. 4. Let's look at this. We need y minus 2 squared to equal y. Right? So we have y squared minus 4y plus 4 equals y. So y squared minus 5y plus 4 equals 0. So that would be y minus 4 times y minus 1. Our limits would be from 1 to 4. Yeah.
Why do we only have regions that are in
Well, we may be partial to them because we're all positive there. Okay. They don't have to be in the first quadrant. They sure are easier. Because, I guess, here's the deal. If we're going to rotate it about this line, wouldn't it be, like, we could have something right here that would give us the same thing. So it's a lot easier to work with something positive and rotate it throughout the third quadrant than to take something in the third quadrant and rotate it up through the first.
Yeah, so it's just the same thing.
Yes, yes. Joe?
Just a weird question. If it's on both sides of the axis of rotation and right with overlap, do you just not
Yeah.
count the stuff that goes over?
We can't do that. We have to have an axis of rotation that is separate from our region. It can't be in the middle of it. Because then you'd have overlaps, and that would get all sorts of weird. Okay? Because then you would have to like worry about where that overlap is going to affect which piece of the graph, and that's too complicated. Okay? Okay, so let me stop the video quick.